Welcome to the GOTO Podcast. Each episode covers the brightest and boldest ideas from the world's leading experts in software development. Tune in for practical lessons, compelling theories, and plenty of inspiration. GOTO gathers the brightest minds in the software community to help developers tackle projects today, plan for tomorrow, and create a better future. Stay up to date with the latest in tech through GOTO's top-rated events held online and in person in cities like Amsterdam, London, Copenhagen, and Chicago, and by subscribing to the GOTO Conference's YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
One of the things that I'd like to do to start off is to lay the groundwork so that we're all on the same plane here. Kelly, for those that are just starting out conceptually with chaos, what is chaos engineering?
Yeah, so I would hope that everybody knows about the scientific method. You know, you generate a hypothesis and you test it and you look at the evidence and then you analyze to confirm or deny the hypothesis. That's ultimately what chaos engineering is. So in the security context, you're basically coming up with hypotheses about the safety of your systems. So that could be whether a security control works, whether a certain type of attack is going to succeed against your systems. You can actually inject a little chaos in order to test that and validate or not confirm that hypothesis, which is really powerful and something we actually haven't seen very much in information security.
When you say inject, you mean literally go into the system and inject an issue into the system?
Yeah, and we do that because it's like what Kelly kind of said. It's really not. Chaos engineering sounds provocative as a term,
yeah.
Right? But really, we're not creating the chaos. The problem is that because the speed, scale, and complexity of modern systems, we're already dealing with chaos. What we're trying to do is create order by proactively, when Kelly says inject, all we're doing is presenting the system with the conditions we expect it to successfully operate under, right? So we believe that under X, Y will happen. So we're proactive. Instead of finding out randomly it didn't work, proactively saying, hey, computer, do you do what you're supposed to do? And that's what we're doing.
And is that the genesis of this book? What's the purpose of the book? What are you trying to do?
I would say the purpose of the book is to bring information security into not just a modern era, but also a realistic era. So we're not just talking about, what perfect security is and textbook security and all of that stuff. It's like, okay, you have a mental model of how you think your security is and how you think the safety of your systems is. How does that actually match up with reality? And kind of looking at the diff between that. As Aaron said, I think most computer systems these days are complex systems, and complex systems inherently have unexpected interactions. And like Aaron said, we can either uncover those when there's a successful attack, or we can uncover those through experimentation. So really the book is not actually just about this experimentation, though that is powerful. It's also about all of the underlying philosophy around resilience and really that ability to recover gracefully. How do you adapt? How do you evolve as a complex, or when you're kind of building and maintaining and securing these complex systems, which is a radical departure kind of from the old way of doing security. So we could have just talked about the experimental part, but really we're trying to do something much bigger as well.
It's interesting. If you think about, you're trying to overlay a mental map on top of a physical. What is the relationship between the two maps?
I like to think of it, you have kind of your mental model of like, here's how the system's going to behave under, a certain kind of stress, right? So you have that mental model. Then you have the physical reality, which, if you look at, let's say, the supply chain attack thing, which is very popular right now, you have this actual interconnection maybe between two components. You had no idea were actually connected, and then an attacker laterally moves, and you're like, oh my goodness, this has completely shattered kind of this mental model of reality. It also can manifest actually when you're performing incident response. You may have assumptions about how your systems behave where you kind of overlook like, oh, maybe actually this is the problem, because that's not even in your mental model of reality. So really what you're trying to do is can almost think of it, in those old school movies, forgive me, which where you do like the rubbings on a rock. It's almost like that. You're like uncovering and excavating, like, okay, here's how it actually looks, not just whatever your preconceived sketch is.
I want to play off of that too. So it takes a while, I don't know if you feel this way, Kelly, but it takes a while when you start doing this and being able to explain it in the right words and message, you're much better at that than I am. All the good writing in the book is from Kelly. But it's one of the best examples that I really kind of honed in on is the concept of a legacy system, right? So what does legacy mean? Excuse me. Legacy typically means it's mission critical, right? That it's typically the flagship application or some derivative of that, or else, and usually it's some kind of mainframe, right? And it's legacy. We call it legacy because we, or we would have gotten rid of it, right? Like it's tech that we need. It's critical to the business. But but the question was, so with legacy systems, we all often associate things like stability, right? That the systems we know how it works. The engineers that work on it feel somewhat confident and competent in how it functions, and it rarely has incidents or outages or issues. But the question I ask is, was it always that way? Right? So we learn, the answer is it wasn't, right? We learn through a series of unforeseen or unexpected surprises, incidents and outages, right? Basically, like Kelly said, we learn what we thought the system was versus what it actually was through a series of surprise events. Now, those surprise events, when we were said, hey, this works differently, so we need to go back and fix it. But remember, those surprises are reflective of pain, right? Customer pain, user pain, people that are operating system, people are using system pain. Chaos engineering, in security chaos engineering, you could think about it as a proactive way of accelerating that process of learning about the system before you encounter pain.
There's a couple things to unravel there. One is, why do people keep legacy systems when everybody's saying, you should be replacing that with the latest and greatest? Usually it's because those systems are critical. It's a critical system that is actually functioning, and the business doesn't want to replace them. But what happens with those systems is exactly what you said, is that there's a corporate memory that's attached to that system. And when you say surprises happen, I like that, surprises happen. As part of chaos engineering, where is the corporate memory? Where is the documentation for these surprises?
Well, I think that's actually a beautiful thing about security chaos engineering is it generates a lot of that kind of shared memory, and ideally, I'm sure Aaron will talk about this, ideally it should be widely shared and transparent, so it's not, this hoarded
Ideally,
knowledge.
Yes, but in reality?
No, but the beautiful thing about security chaos engineering is, again, rather, incidents eventually fade into memory, right? It's a memory of the past, and people stop kind of learning the lessons of those. But if you're kind of continually practicing, conducting these experiments, confirming, checking your hypotheses, challenging your assumptions, if you're doing that on a continuous basis, which is what security chaos engineering is all about, then you're kind of continually generating this new kind of shared knowledge. You're continually keeping that memory fresh, which is really important. And I think, to your point, part of the reason why people do stick with legacy systems is because they do understand them. I think it's a very, very understandable, natural human tendency. We want to understand the world around us. It makes us feel safer. It makes us feel more in control. And again, with security chaos engineering, rather than having that long lifespan of legacy system, which is one way to kind of understand, again, all of the different interactions, the way the system works, you can conduct experiments and kind of generate that same understanding. It can actually give you, even though chaos sounds like there's not a lot of control, it can actually at least impart a greater feeling of control because you have that greater understanding about how your system behaves in practice.
And furthermore, is that when we're doing this to proactively, so during an active incident or surprise event, right? Because if it wasn't a surprise, you would have just fixed it before it became a surprise, right? But during an active incident, that is not a good time to learn. People are worried about being named, blamed, shamed, right? I knew I should have pushed that code. I knew I shouldn't have done X, right? I'm going to get fired, right? People are freaking out, right? Do you think, when you're the world around you is on fire? You really don't, right? But the world is not on fire when we're doing chaos engineering or security chaos engineering. We're proactively trying to understand the system. We can learn. We don't have the blinders on. We're not looking back. A lot of times when the incident or an outage happens, we look. Kelly and I expand on a lot of these concepts around hindsight bias and the sharp end versus the blunt end and a lot of it comes from Sidney Decker's 20 years of airline accident investigations. Right. We go into the world of cognitive sciences, safety engineering, but but is that if you know the outcome of the event, you look at the events that unfolded up until the outcome completely different, right? So, but what we're doing is proactively trying to understand the system with eyes wide open, if that makes sense.
Mm-hmm. As you both were talking, it came to me that if documentation is done properly, if the documentation of these surprise events are done properly, it actually becomes part of the system itself and is actually a way for the system to respond to future incidents of the same thing. Is that part of the process here?
Yeah, we definitely, the way we characterize it is like building muscle memory for incidents. You can almost think of it like, again, one of those like training montages, where you get the fake like people fighting you, so for the real boss fight, like you're all ready. It's very similar to that. You're basically building that muscle memory, making sure that when a real surprise happens, not these kind of like injected chaos surprises, you have a much greater sense of how to handle it and how to respond gracefully and not experience the burnout and stress. I think most responders, whether that's performance incidents or security incidents, most of them experience that kind of burnout and stress. So that's our goal.
It's still, though, if you're thinking of humans as part of that process, that's the problem. And I'm thinking that if chaos engineering is done properly, the system is the one that responds, not the humans responding. Is that
completely disagree.
Okay, good.
Yeah.
I don't think humans are the problem. I think that's kind of like Aaron was saying, we can see this across all sorts of disciplines. There's, I think there was one incident where the relevant alert, this might have been a nuclear plant, maybe you remember, the relevant alert was on the backside of one of those, old school big panels at the very bottom flashing. And they said, well, the operator should have known. It's like, really? Because there were 100 other lights flashing. They should have known that the correct one was like on the other side. It's ridiculous, right? You can see in other industries where they blame, an operator for, not knowing that there was like a truck whose beepy thing backing up was broken, not realizing that it was broken and looking around to see. Like, we love to blame operators because we're removed from it. We're not in the situation, and I think it's very much part of the just world hypothesis. We don't like the idea that random, terrible surprises can happen, and so it makes us feel better. You could say, well, actually, it wasn't random and terrible. It was because this operator did this dumb human thing. So I think if we actually look at the history of incidents, humans are ultimately often a source of strength because computers are largely, not entirely, very deterministic, right? Humans are the ones that can be innovative. They can be nimble. They can be flexible in their thinking. They can respond in very adaptive ways. And so part of what we're trying to promote with information security, right, has totally blamed the human most of the time, dumb users clicking on links, all that stuff. But what we're saying is actually, well, humans behave in very human ways. Maybe we should be designing our information security systems and our processes and procedures in a way that understands that humans can be very adaptive, but also they have finite attention, they have finite time, they have all these sorts of production pressures and constraints. You got to ship software quickly, all that stuff. So we need to be very empathetic with the human. We also need to view the human as a source of strength. How can we make sure during incidents they do feel empowered to have like nimble responses? I'm sure Aaron can talk about some of what we've seen kind of more in the wild on that front too.
That was a really great answer. I think so. I couldn't echo it even more. I mean, we read a lot about this. The humans are the solution. I mean, it's humans that I don't think we're ever going to have machines writing all of our software for us. It's one of the ironies of automation also that you can't really, that when you write automation, you need less humans. You actually need more because somebody's got to maintain the code, somebody's got to write new code, right? It's like Kelly said, the word adaptive, right? There's this term in resilience engineering called adaptive capacity, right? And it's basically so humans have more ability to look at different things and figure out what's going on and make decisions, and we need to empower. Part of what chaos engineering, where it began at Netflix, was to put better information in front of engineers, right? Turns out if engineers have better context, so Netflix was very big about context over control, right? The more context you have around a problem, it's more likely you can solve it, right? I think Charles Kettering once said, a problem well defined is half solved, right? And a well defined problem, it's easier to solve. That's what engineers do. They solve small problems.
And I think there's an important distinction here also between uncertainty and ambiguity. Computers could often be good at resolving uncertainty. That's just a lack of information, like collecting all the relevant data points. But there's also ambiguity, and that's you can have the same set of data points, but there are two different ways to interpret them. And what's the right interpretation in context? That really depends. That's not something, at least yet, we've really taught computers how to solve. For instance, take an intensive care unit, right? A doctor sees that there are two different patients. They have one maybe needs palliative care, one is facing something terminal, the other maybe could be cured, but the other one came in later. How is a computer supposed to decide that? I don't think we want necessarily computers making those kind of decisions, right? That's ambiguous. You have all the data that you could possibly have, but what is the right decision? It's very unclear. And in a lot of these incidents, again, you see across industries, and certainly in the what I call computer system realm, we see that roughly what we call human error is because we think that the human operator should have resolved that ambiguity in a different way, that there's clearly the right way, but maybe not in context. So I think we have to be really careful that more information won't necessarily solve things, because a lot of these choices are not just, there's one right answer. It could be, the same data points, again, in a slightly different context could result in a completely different outcome. Again, we need to empower the operators to make the best decisions they can with as much context as possible, but they aren't the problem, right? There's always going to be mistakes. There's always going to be, I don't think we're ever going to be able to resolve ambiguity ever. That's a judgment problem. And I think we see, not to get too philosophical, but I think we see across society a lot of times we do try to solve kind of problems of judgment with metrics, and I'm not sure how well that's working out because we just gave them metrics. Is that better? I personally don't think so, but.
All right. You have both used the term security chaos engineering several times already. Is it a coincidence that that's the name of your new book?
No. So part of it, we recognize that there's a branding part of it, right? If we're introducing or trying to usher in this new era of information security, which we think is more pragmatic, more aligned to kind of, again, the realistic models of how systems and humans in those systems work, we need a catchy name. And security chaos gets people's attention. Like Aaron was saying, chaos, it's a pithy name. It's one that people are like, wait, do we actually want chaos? And the answer is yes. So that's one part of it. We also thought it was really important to extend that underlying discipline of chaos engineering, just because that is something that has been well practiced more on the kind of broader DevOps community side, which is obviously relevant to our conversation. So we're bringing it and looking very much at how it applies to information security as well. So we could have called it, something like human sensitive, resilience engineering for system safety, but security and chaos engineering is much pithier.
So who called who?
I think I was already writing a book because that's just what I do in my free time. I just love writing. And I think Aaron reached out to me because he had seen I was talking about security chaos.
It was the Black Hat talk. It was your Black Hat keynote you did with Dr. Kulaforsk, and I'm like, whoa, we gotta talk, right? And then, I think I came up to New York and we talked about, we had all these things we want to write about, and I think I must have filled up several pages of notes. I was like, okay, we have maybe several books here, because there's there's so much depth beyond the practice of security chaos engineering. Because one of the things I was wondering early on so I wrote the first open source tool that applied Netflix's chaos engineering to cybersecurity. And
that tool was?
Chaos Slinger. Still out on GitHub, but it's deprecated. United Health Group has their own version of it, and I'm no longer there. But it's one of the things that I was trying to figure out also is what pointed me to a deeper understanding is why are these chaos experiments always unsuccessful, right? Because we only do chaos engineering experiments, security or not, for under conditions we expect the system. We think we're right. We're introducing the conditions we expect the system can handle. Right? We're not trying to introduce randomness or trying to introduce it's not a monkey in a data center pulling cables. Everybody loves to use that example. That is chaos, right? That's mayhem, right? What we're trying to do is introduce the conditions we expect the system to operate under. But I started doing that, and the system almost never did what we expected it to, right? So why are we wrong about how our system? Because we're basing all of our engineering practices on hope and luck, right? In engineers, we don't believe in hope and luck. We believe in instrumentation, feedback loops, data. Like, we believe in those sorts of measurement, these things that tell us it didn't work, why it didn't work, and how we can improve it. And so I started in suit. I started following some of the work being done at London University and with Casey Rosenthal and Nora Jones, and about resilience engineering and safety engineering, the cognitive sciences. There's a human brain behind these computers, right? And they interpret things differently. Anyway, Kelly and I were kind of both, like, we've been reading a lot about these concepts and trying to, what we've been trying to do is also extend some of the great work being done by Dr. David Woods and Richard Cook and these people that have been, David Woods created resilience engineering after Prima.
Because the way I came about it was actually slightly different, which I started actually with earthquake resilience of all things, to look at how buildings are actually designed. And there's this one quote that still sticks with me, and it's Dr. Elizabeth, I think, Howe, who's a geologist from what I remember, and she says, like, a building doesn't care if the earthquake was predicted or not. It's either going to stand up or it's going to fall down, right? And I thought that summarized so well, or pattern matching to information security, it summarized so well. At the time, it's a little less now, but at the time there was so much effort put into how do we predict breaches? Like, how can we predict what's going on, and all this data science going into it? And it's like, it doesn't matter. Like, either your system is going to be resilient against attacker or it's not. Like, either you're going to experience a breach or you're not, or you're going to experience downtime or you're not. But there was really no one talking about it in those terms. Information security, so I delved more into kind of natural disaster resilience, ended up also going into David Woods because he kind of spans a bunch of disciplines, and looking into resilience across all these different domains. And actually quite late I discovered that, this has already been kind of described on the chaos engineering side, and I found that fascinating. But I think there is that kind of underlying issue in information security, which I'm not sure how often the software engineering community more broadly understands, but in information security, it's very difficult to measure what success is. And as a result, it means that we have stuck with strategies for decades that just don't work. But that's the folk wisdom, and that's how it's always been done. And if we can't measure success, we're never going to improve. And it seemed like being able to conduct these experiments, which, by the way, computer people are very lucky. We can't conduct these sorts of experiments in, like, nuclear power, right? That's unethical. And there are a bunch of domains, even in macroeconomics, we can't just inject a financial crisis to see what happens across the system. So in computer science, we are incredibly lucky that we can kind of inject this kind of, again, what I call controlled chaos in a way to understand better how our systems are going to behave. And in information security, that is so powerful because we can finally see, hey, are our strategies actually effective? Do they actually operate the way we think they're going to operate? Can we actually, again, build this muscle memory to respond to incidents better? So that's why we think it has the opportunity to actually start, we can start to see an information security industry that maybe is a little more pragmatic and constructive rather than just, hand waving and kind of like the shamanism of old.
And AI is not going to solve all your problems.
Correct. Yes.
So
stop that.
Let's talk then about specifics.
Sure.
We've talked in generalities about what's going on. How has this been applied? I think in the book you've got 2 examples to start with, right?
We have a few. We have quite a few case studies. We've been lucky that there are a bunch of people working on this. Aaron definitely has seen a lot of these up close. One of my favorite ones is actually, I believe it's Open Door in the book, talking about with logging pipelines. I think it was
Prima Varani, I think, right?
Prima Varani, yes. So I think it was, I forget which congressional committee investigated one of the, I think it may have been the Census Bureau had a breach. And what they discovered is that logs had been sent nowhere, I think for it was like 18 months, maybe more.
Logs had been sent nowhere?
Nowhere. They were being sent out to I believe it was a SIM that had been decommissioned or something like that. So they were broken for 18 months. They had no idea. And that was one of the recommendations, obviously, in the report. I thought they were a little too shamey, again, with human error, but they were like, probably you should have your logs actually going somewhere real. So in this case study by Prima, it's basically like, can you be sure, like, log pipelines are the lifeblood, whether that's like site reliability engineering or obviously on the security operations side, responding to an incident, you need your logs, you need that visibility. So you can test like, hey, are log pipelines actually going to continue operating under these various scenarios? You want to be able to validate, like, yes, we can be confident that our log pipelines are going to be able to provide it.
But isn't that a one-off? I mean...
No, I think if there's honestly, like, if someone was going to spend time on security chaos engineering, I think control validation is a good one. It's a response, but observability in general. Observability, in my opinion, is the other half of this big problem we're Kelly and I are kind of attacking with security chaos engineering. Observability in software security sucks. It's horrible. It's horrific, right? So we put all this time and effort into detective and preventative kinds of things, hoping that when they happen that the technology works, the humans are prepared, all these sorts of things, right? Well, with the security chaos engineer, we're introducing those conditions, that signal as soon as we inject that condition for the preventative or detective kind of logic to fire upon, we can look at the technology. Did the technology work the way it's supposed to? But other things we can look at now that we're looking at it from the other angle, we're not looking at after the fact, we're looking at it proactively. We can see, did the systems actually give us log data, event data that we could read and make sense of? Had this been a real problem, would we have known what to look at?
Well, still, we'll go back to the point where if you have never seen a problem where logs are being sent nowhere, you have no way to look for that. You wouldn't even know to look for that.
I don't think that's necessarily true, because we have the case study in the book of like, hey, you should worry about this. I think there's also a great database, which could GitHub reach, though, of just like postmortems and things going wrong. And we certainly, part of what's in the book is we recommend a whole boatload of experiments to conduct as well. But I think Aaron's point is really, again, it's the scientific method. I think it's very reasonable for people, you can give your hypothesis is like, when, this port is opened up, we expect, the security engineering team Slack channel to receive an alert. That's something I think you're just documenting, like, here's your expectation. And what may happen in practice when you conduct the experiment is like, the alert didn't show up. Why is that? And then when you go and investigate, then maybe it's because like something's messed up in your your logging pipelines. So I think I think it's always good to come back to that scientific method where you don't necessarily have to know the counterfactual of like, oh, hey, like log pipelines can be broken. What you do know is you do expect to receive an alert. And from there, you can kind of untangle. And that's really, again, the beauty of security chaos engineering is it's about that mental model. You have this mental model of how your system's going to behave kind of end to end, and how does that actually measure up in practice. So you don't need to specifically test like, hey, are logs being sent nowhere? But you can test, do we have alerts? And to Aaron's point, like, if we want to investigate deeper, can we access the logs? And then maybe you're like, we can access the logs. That's interesting. Again, it is much better to do it in this kind of controlled chaos experiment rather than when you actually have an attacker that's up in your systems, right?
Real world example, meaning the situation where the HVA system was hooked up to the point of sale systems and nobody knew it. That example. Would chaos have done anything about that? Or notified anything about that?
I think it could, because chaos experiments, it depends on the experiment, but a lot of times it can, again, excavate those kind of flows, kind of like, if you think about the tributaries underneath once you kind of unearth the system. I think very similar to, you have control flow within like a particular program. You also have kind of interaction flows and data flows within your application, within your systems. I think in theory, you might have been able to see like, there's relatively tight coupling, because if you injected some sort of, fault into one system or the other, maybe you would have seen, we're getting some sort of reaction in this other system, but there shouldn't be, right? So I think it's certainly possible. And again, our view is that you shouldn't, like you said, you shouldn't just do a one-off experiment. That's a good way to start. But ideally, you're trying to automate some of this. You're trying to kind of like continually test your hypotheses and eventually get a little more sophisticated over time. So my view is certainly, if those systems matter to you and you want to conduct, I would imagine you would want to conduct experiments in them, then probably that coupling would have been uncovered. But I don't know what you think, Aaron.
No, I mean that's a great answer. It's really, this is not magic stuff. This is rooted in the core components of all science and engineering, right? I mean, we're providing a method for instrumentation, right? And how often are you actually, looking at the system with that kind of perception or that kind of angle? We're always looking at it after something bad happened, and we're worried about damage control, right? Like, we're not worried about really what happened, and we always love to believe there's a root cause. What we're trying to do is proactively understand the system. You may be like, hey, what the heck is this error coming from? Looks like an HVAC system.
The problem, though, at this time in history, is the complexity and scale at the enterprise level of problems like this. It's inconceivable what that complexity is. It's grown beyond human comprehension. Where does chaos fit in to make this, I would say, palatable, but that's not the right word.
No, I mean, that's the whole point of chaos engineering. So if we had perfectly linear systems, you probably wouldn't need chaos engineering so much. Because ultimately what chaos engineering is doing is undercovering, again, the interactions in the systems. And I think the hard part about complex systems is because you can't really reason about them as well. You can't build that mental model once they reach a certain level of complexity. And in large part, kind of like your HVAC system with the point of sale system, it's because of those interactions between components. It's another reason traditional security is not going to catch that either, right? Because it's looking, does each individual component have, from this list of vulnerabilities, they're not looking at those interactions. What chaos engineering is saying is okay, that's not enough. What we need to do is, again, build that better mental model about how our systems are behaving. And that's precisely what you do when you conduct an experiment, is you are able to uncover, there seems to be coupling over here, and some sort of fault in this component actually ends up kind of trickling through to all these other components. That's not something you can do with basically any of the kind of security testing methodologies today, but you can do when you conduct chaos experiments. We're certainly not saying it's silver bullet. Your first chaos experiment, you're going to have this beautiful new architecture diagram of all of the interactions in a complex system. Point is, though, over time, I like to view it as you're piecing together this mosaic in a way that you couldn't before, and that's really powerful.
One of my missions on at least in speaking about this stuff and writing about it, is trying to educate the security world about complex systems. I mean, and that's where a lot of this, the depth behind the security chaos engineering comes from: resilience engineering, safety engineering, cognitive sciences. If we don't start to understand this problem, everything we're doing today is almost irrelevant. I mean, it was okay, kind of, when we had the 3-tier app, right? And we had far fewer components. But now with microservices, public cloud computing, the continuous delivery, continuous integration, DevOps, we're now delivering value to customer faster than we've ever had before. But also, software never decreases in complexity because it's changeability, right? So software, if you say you have a complex system, software system, and you want to make it simple, how do you do that? You have to change it, right, to make it simple. Well, the act of changing it is, remember, the relationship between change and complexity, right? So you're actually just moving the complexity around. So it's not about complexity and removing it, and it's about learning how to navigate the complexity and understand it. And that's what we're doing with this stuff, and because we don't get better, this problem is a gnarly one to tackle.
Yeah, and I think that's actually a really good point. That complex systems, computer systems aren't the only complex system, right? It kind of goes back to my point. In some ways, computer people are kind of spoiled in that we can actually wrangle this complexity in a way you just can't in other disciplines, because it's unethical, or it's just one of my favorite anecdotes is in nuclear power plants, they have to, in their own pipelines, literal pipelines, they have to deal with the fact that clams will start to grow. We don't have to deal with stuff like that in computer systems, but it's just mind-blowing that the system that, if it experiences a catastrophic accident, could kill potentially hundreds of thousands of people. One of the ways that could happen, the root cause could be clams growing in the pipelines, right? So I think, again, it's not like we're inventing this concept of complex systems. Computer systems aren't the first time we've had to deal with complexity. If we can draw on all this incredibly rich research over decades now of complexity, whether that's in ecosystems, nuclear power plants, healthcare, mining, marine systems, air transportation, it's just everywhere, even human brains. We can leverage all of that expertise in very hard fought kind of lessons learned in order to improve, in this case, the discipline of information security as it pertains to computer systems.
And on that thought, I was thinking about the human body when you were talking about nuclear. Human body is also a complex adaptive system. And I had recently recommended to a security researcher to read How Complex Systems Fail by Richard Cook. Well, it's only 2 pages. When you read it, you think it's about a computer, right? It's actually about the human body. He's writing about the human body, but it makes total sense for computers, right? Blows people's minds, because after this woman had read it, she reached out to me she's like, that's an amazing paper. I said, okay, did you know that he's talking about the human body? Mine was blown, right? But I guess what Kelly and I are trying to relay here is that we're going back and looking at what other people have done, right, to tackle these problems as we walk into this world, in the world of technology, and now arguably the powers have shifted. Technology now is facilitating a lot of these core components, and we have a responsibility as stewards of them to manage them effectively.
One of the dilemmas, though, as part of the whole process of complexity, is you mentioned speed, Aaron. Things have to be faster and faster. But there's a trade-off there, because there's a creation of potential vulnerabilities because of the speed that things are changing.
Not sure I agree.
You never agree with me.
I know. That's me as a person. I think I love Dr. Forsgren's research, and one of the things she uncovered, and this was looking at the accelerate metrics, or DORA metrics, so the 4 golden signals for DevOps. What she found is that speed and stability are actually correlated. Think about very simple case in information security with patching. Like, one of the root causes of a lot of breaches is that a patch didn't happen, for 18 months or some egregious amount of time after the patch was released. Why is that? Because they couldn't actually ship software quickly. If you can ship changes on demand in your software, you can ship patches on demand. That flexibility and that speed is actually vital in order to be able to implement security changes as well. So I think when you look, and this is similar in other disciplines too, that speed and stability are often correlated. Not always. If you look at seat belts in a way, and brakes, I think Sunil Yu has mentioned this. If you look at brakes, it allows us to go faster in a safe way. So I would certainly argue that we shouldn't view speed as inherently bad for safety. I think sometimes safety is necessary to go fast, but I think the bigger issue is around the mental models. If we're going quickly, and if we're able to kind of build things at a scale that we can't really reason about in our brains, that's where the mental models start to break down, because you're having to iterate on your mental model constantly. And that's, again, a vital kind of benefit of security chaos engineering, is it allows you to keep evolving your mental model. It keeps, after a year of changes in a high kind of velocity organization, that the way your system behaved at day, January 1st to December 31st is going to be radically different. If your mental model is the same as it was on January 1st, that's a huge problem. But if you're kind of continuously conducting these experiments, then your mental model is also evolving along the way, which is really important.
You've used the term mental model numerous times here. How is a mental model actualized? What does it look like?
I think that's different in everyone's brains. But I think when it's actualized, I think architecture diagrams is a great example of that. Is very much the software architect or designer's notion of here's how the system actually looks. Maybe behaves if they have flows between them as well, depending on the architecture diagram. If you looked, and there are some tools that help with this, obviously security chaos engineering helps uncover this as well. If you look in practice, though, probably after a year in production, that architecture diagram doesn't actually reflect the reality. There are other things that you would have to extend it to include other systems where it's talking to, all that good stuff.
You're smiling. You just like hearing her talk.
I do. She's brilliant. So I was, prior to my current role at Verica, I was the chief security architect at United Health Group, and that's where I started doing a lot of this stuff with security chaos engineering. And she's so right. When people come to me, a solutions architect and a data architect will come to me for the same system and show me 2 different diagrams, right? Often the system never actually reflected that. That was just how they believed the system to work. Neither one of them are correct But and when we say mental model too, think about the number of mental models you have running, the number of humans and their perceptions of things. So let's say you have 10 microservices in a modern application, right? You've got payments, you've got billing, you've got reporting, you've got 10 of them, right? You don't actually have 10, right? But usually for each service, there's a team of engineers, right? There's an engineering manager and probably some engineers as part of that, right? And sometimes one team will handle 2, but usually just 1. So you have 10 sets of humans working on individual microservices. Those microservices are not independent. They're dependent upon each other for functionality. So all these things have to work together. Let's say they're doing things like CI and CD and DevOps. They're making, let's say, 5 changes a day per microservice. Maybe they're on the same schedule, maybe they're not. They're all deploying changes that affect each other, right? In this post-deployed world. So imagine, just imagine the number of changes in systems impacting each other. All these teams see their world of the system post-deployment differently, right? So it's a shared mental model. So if the humans that are operating system don't understand the system and their mental model, it's hard for, this stuff's hard. Complex systems are hard, right? But we have to get these engineers that are operating these critical complex systems better information, better context, so they can be more effective at what they're trying to do.
Let's put that in context of the book. You've got a 90-page book here, and you have another one coming out. What's the purpose of the first book here, the first 90 pages?
It is, I would say it's a something bigger than an appetizer, but maybe not like a big steak sort of meal, introduction to security chaos engineering. The idea is you get a kind of bite size into the underlying philosophy, enough to get you started and to rethink kind of your security programs and practices, procedures, all that good stuff, as well as to be able to get started with how to conduct experiments, which Aaron very much led, as well as some examples of experiments that might work for kind of the way most systems are built. So for instance, thinking about how to inject faults into automation servers, orchestration control planes, just vanilla sort of Linux servers. We have a bunch of cool experiments there. So it's really a how-to guide for, okay, you're early in your journey. You think maybe more realistically, you know that something is off in your security program. You don't seem to be getting results. Why is that? We talk about that a little bit because we compare what I call security theater, which is kind of the traditional way, where you just do things for the sake of feeling like you're doing things about the security problem, then the security chaos engineering way. So it's enough for you to see, okay, here's some of the reasons why it's not working today. Here's maybe how we can reimagine it, both from an organizational and kind of cultural perspective, as well as the philosophies behind practices. Then here's how we can get started in practice with some experiments. What the full book's going to do is going to extend that. It adds much more depth. It's going to be a full-fledged just guide for not just how to build kind of a brand new kind of modern security program that works for this kind of modern era of complex systems we're talking about, but also many more case studies, because that's one thing that is very clear from kind of the audience is they want to hear more from a diversity of kind of industries and organizational types, how has it worked for you? And that's something, there's going to be a large chunky part of the book that's dedicated to that too.
One of the ways that you and I have talked about, Aaron, when we were together in Singapore, maybe even Sydney, is that people learn from failure, other people's failures, hopefully. Where does that fit into what you guys are working on here?
Well, the underlying philosophy of security chaos engineering is that failure is, a great teacher, and that failure is inevitable, so we might as well learn from it.
Opening,
I think it might be the first sentence.
I think it's Yoda.
Yeah.
Teacher, failure, the best is
whatever
Yoda's speech is.
Is that somebody who was Steve, I forget, Dr. Steve, one of Gene Kim's friends, said that failure is the default state of the system.
Oh, that's Dr. David Woods, and that's Woods, one of many Woodsisms. But he loves to say the system was never broken; it was designed that way, right? Right. So failure is just a core component in all human evolution. Right? It's how we learn. We fall down, we get up, and failure is is a core component of how we grow and build better systems. And what we're doing, that's why we open up the first book with it. Probably going to open up the second book with something similar, just because people need to understand that, like, we're not very good at this stuff we're doing, right? And it's okay, right? We're trying to get better, and this is a way this is a methodology, this is a discipline you can adopt to help you get better. And understandably, so what I love about chaos engineering as an engineer is that, like, the confidence you build, right? Like, I'm not just putting something out in the ether, in some system, some control, some firewall, some whatever, hoping that it works when I need it to work. I'm actively introducing the problem it's supposed to work under. I know it works. Knowing it works creates just a level of confidence when something bad does happen in the wild, that you know that you're not fully covered, but you have your confidence that you can handle those sorts of conditions.
There's also a meta point that maybe gets into more like cold corporate territory. But most traditional security strategy today is based on trying to prevent failure, which is impossible, as David would say. So one, you're wasting a lot of money, what in the economic sphere is known as opportunity cost, both the time and money that you're spending on trying to prevent failure from happening, which is impossible, could be spent on actually preparing for that inevitable failure and making sure that you're recovering gracefully and that the impact to the business is minimized. That's not where the focus is today. It's trying to minimize risk, which is very nebulous, to zero, and it doesn't really work. So again, from that cold corporate perspective, like, we're just wasting just like a boatload of money right now on trying to prevent failure, which is impossible. The meta point here is that actually results in failures of security programs. By trying to prevent failure, we're actually introducing failure at the macro level in our security programs, which is slightly poetic, but very unfortunate for the users whose data we're not protecting very well. So.
You both have mentioned Sunil Yu a couple times here. Who else should people be following? Sunil is an obvious one. He does great stuff.
I think certainly following people who helped pioneer chaos engineering more on the kind of like performance side of things. Well, some of Aaron's colleagues.
Casey, for one.
Casey Rosenthal he created chaos engineering at Netflix. And then there's Nora Jones. She did the keynote for reInvent years ago. There is also, David Woods, Richard Cook. You've got... for security chaos engineering, you've got Jamie Dicken. She's doing some amazing work. She wrote the Cardinal Health pieces there.
There are also
Mario Platt. Oh, go ahead.
Mario Platt for sure. There are also some people that are kind of in adjacent spaces, which again, security chaos engineering isn't just about the experiments. That's an important part of it, but it's also the underlying philosophy. I would say B. Hughes is someone who I know. She gave a talk, I think back, in 2013, that was all about like, hey, maybe we should actually be working with the humans in our systems, and maybe they matter, and maybe that just telling them, hey, you made a mistake and you're wrong, isn't particularly helpful, and how can we become more confident during incident response? And I know she's also continued to publish and talk about I would say contrarian takes to traditional security, which I think is an important thing. Because again, security chaos engineering is all about challenging your assumptions. I think it's important to follow thinkers who are challenging those assumptions about what I would call status quo security.
To kind of close the loop here, what are you hoping to accomplish? What do you hope people will do once they've read the book? I
certainly hope if I had... it's hard actually on a wish list. I have a very long wish list, but getting away with human error as a reason for incidents, as a root cause of incidents, I think would be huge, because from that trickles so many different changes. If we stop thinking that it's an individual human who caused this massive incident, if you assume that, then you aren't looking at the design, you aren't looking at you're completely ignoring the fact that your mental model may be totally off. You just think, well, we need to just like punish the human or create more restriction around the human. Nothing's ever going to get better. So that's one of the key items there. At a broader level, other than, world peace and harmony, I think it's ultimately we want information security right now is honestly letting down the modern discipline of software engineering. I think that's safe to say. And so we would very much like to kind of usher information security into the 21st century in a way that's actually going to make systems more resilient, not just keep spending money and making a lot of people kind of very well off and, give them more importance and thought leaders. We want information security that actually works, not that just does something for the sake of doing something.
I'm glad you said the human error bit. That was going to be mine. No, but I would also add root cause to that, because the root cause does not exist. It never has. It's a fallacy, right? There's no, take this example, right? Name one reason why you as a person, root cause, are successful, right? You can't, right? If you can't name one reason why something's successful, you can't do the same for why it's not, right? If you ended human error as the root cause of an incident or a problem, that's the beginning of your investigation, not the end, right? So I challenge more discipline in that world, but and I want to just build off what Kelly said too. It's it's not that there are humans that lack the ability to try, right? There are passionate people trying in this craft, trying to do good things. It's what we're trying to do is lead them in a direction, I think, that targets the real problem at heart, which is complex systems. And I think what we're trying to also achieve is give them a way of the philosophy of thinking about think about what we do in a different way, but this is not Kelly and Aaron just making stuff up, right? This comes from the world of safety engineering, how they've been able to pioneer and transform how they handle airline accident investigations or nuclear power plant incidents. And so we bring that strength into from a philosophy of why we're saying you should think about doing this differently for this reason, and furthermore, we follow that up with in the larger book that's coming towards the end of the year is a deep how to write these things. This is not super advanced engineering. This is not AI. This is not the blockchain. This is not some magic engineering that's you can pour on your stuff and it'll solve everything. This is a basic level of instrumentation, similar to testing, right? Where we're going to walk through several different examples, different kinds of systems. You're going to have case studies from government, case studies from healthcare, from banking, from startups. So everybody has an idea of how this stuff could be applied and how to write them. And we look forward to seeing more stories unfold in the community.
Importantly, it's going to be inclusive. This is not a movement that can be solved just by information security professionals, which I agree. They just need a kind of better way to conceive the problem. It's also for software architects, software engineers, whether that's leaders or people kind of, building systems day to day. We actually will have chapters covering each kind of phase of the software delivery lifecycle. So if you're just like architecting a new system, you can open up the architecting and designing chapter and be like, how can security chaos engineering help me make this system more resilient against attackers? So we want it to be both practical, grounded in principles, and have ample examples so people feel really confident about, I guess, interestingly enough, being more confident in their systems. So.
The book is out, Security Chaos Engineering.
The slim book is, and then the full book with the animal on the cover, which TBD. We're very excited to see what will be given with the animal. That will be out, I believe, later this year.
Oh. I think the first book is written more to be to be read from end to end, whereas I think the larger book is much larger and it's more reference oriented.
Great. Thanks to you both.
Thank you for having us.
Thank you.
Yeah, thank you.
Thanks for listening to this episode of the GOTO podcast. Head over to gotopia.tech to discover lots more content from the brightest minds in software development.